Welcome back to my course Aspects of Biochemical Engineering. Now up till now I discussed mostly on this we started with this reaction kinetics, then we started and we discussed the reactor analysis, then we discussed the enzymatic reaction kinetics, then we also discussed the mobilized enzyme system, then microbial system, cell growth, substrate degradation and product formation, and last two lectures I concentrate on scale up of bioreactors. Now this present lecture plays this is a very important aspects as per bioprocess is concerned. This is the transport phenomena in bioprocess. Now transport phenomena, the term itself tells kind of transportation and kind of transfer that how taking place. Now there are different type of transfer that take place in the bioprocesses. So that can be divided into three different types. One is called momentum transfer, another is called heat transfer, another we call the mass transfer. There are different type of transfer processes we have, and we try to discuss how this process plays the important role in this biochemical process. As for example, that mass transfer process particularly I can tell you plays important role as per biochemical that aerobic fermentation process is concerned, because I told you that major limiting factors for the aerobic fermentation process is the dissolved oxygen concentration. So since oxygen is sparingly soluble in water, so we shall have to increase the solubility that the dissolved oxygen concentration, that directly related with the mass transfer, that how you can we can do that. Another important aspect is the heat transfer, because as you know that any kind of fermentation process, that the microorganism, they are very sensitive to the environment, and since they are very sensitive to the environment, that what you have that any kind of temperature, if we shall have to maintain a particular temperature so that your organism can give the maximum performance in the reactor. Because if your organism work well, then and only then you can expect the desired amount of product formation to the extent you are expected. So to maintain the temperature, naturally the heat transfer plays very important role. And as you know that in the biochemical processes, that most of the processes they are exothermic in nature. Now exothermic means the heat liberating, am I right? So heat liberating, that means there is every possibility that temperature rises. But that in case of summer, what is happening, since we are in the tropical country, our ambient temperature increases as high as 40-45 degrees centigrade, and maybe our fermenter temperature required maybe 33 or 35 degrees centigrade. So it is quite less. So so question comes that the cooling effect, that requirement will be more. So we shall have to pass some kind of chilled water just to control, or we shall have to pass more water as so that temperature we can maintain. Now in case of winter, the ambient temperature may fall as low as 15 degrees centigrade. Then also you have to increase the temperature to some extent, because there will be always some kind of heat loss that take place in the fermenter. So heat transfer plays very important role, and momentum transfer also plays very important role, because that you have to, when you study any kind of fermentation process, you have to keep the cells in suspension, and for the suspension of the cell you have to use a kind of starter, so that the cells remain suspended and freely interact with the substrate and give the product. Now let me start with this, that the subject deals with the movement of different physical quantities in any chemical and biochemical processes. So that is the movement. I told you three type of movement is there, as the momentum, heat transfer, and also you have mass transfer. Now describe the basic principle and law of transport, and also describe the relation and similarity among the different type of transport that may occur in any system. Let us see the classification of the transport phenomena. This is the classification of that. We have three different classification: momentum transport, energy transport, and the mass transport. What is momentum transport? It deals with the transport of momentum of fluid, and is also known as fluid dynamics. For example, blood circulation in the body, mixing phenomena in the bioreactor. Both that comes under the momentum transport, because this is very easy to understand. The mixing phenomena I just explained. The energy transport deals with the transport of different form of energy in a system, and is also known as heat transfer, as for example sterilization, because I forgot to mention that sterility of the reactor is very important, because we want to grow our desired organism in a particular environment so that we can get the desired product. And also temperature control in the bioreactor. Just I pointed out that organisms are very specific with respect to temperature. At a particular temperature they give the maximum product. Mass transfer deals with the transport of various chemical species themselves, and also known as mass transfer, as for example oxygen transferred from the bubble to the aerobic microorganism. So you know that from this we can easily understand how crucial is the transport phenomena as per biochemical processes are concerned. Now when you try to solve it, we come across different physical quantities. Am I right? And what is the one is scalar? Scalar means it has some values, as for example temperature, pressure, and concentration. But vectors, they have some direction, velocity and momentum and force. And second order tensor is the stress or momentum flux and velocity gradient. So these are the different quantities we will be using during describing this transport phenomena. Now if you look at that three level study, one is macroscopic level, another microscopic level, and the molecular level. In the macroscopic level, that the inside the fermenter, what is happening if you study something like this. And now here inside that you might be using some kind of cell, or in a particular portion of the liquid you want to study in details. Then we have this microscopic analysis. And then molecular level means how the molecules inside this cell they are interacting with each other and give the product. So that three different level of studies are there. Now three axioms are there. Mass is conserved, which is lead to equation of continuity. Momentum is conserved, which leads to equation of motion, and energy is conserved, which lead to equation of thermal energy. So these three equation collectively called governing equation. So this on the basis of mass conservation, on the basis of momentum conservation, on the basis of energy conservation, that we can try to solve this. Now general statement of transport processes, how you can do that. Rate of transport process is the driving force, but is defined by resistance. So driving force means, suppose you want to heat some liquid. What is the driving force? The driving force is the temperature difference, and resistance is the media that they hinders that that flow of the that heat. So that now that this driving force we can explain like this. Factors make that the driving force is the momentum transport is the velocity gradient, and microscopic it may be microscopic, molecular, and velocity difference. The momentum, as I understand, that mass into velocity. Am I right? So the mass is the velocity gradient that plays very important role. Energy transport is the temperature gradient. We know MST. MST is what that mass is specific heat and temperature. The temperature gradient plays very important role. And driving force is the mass transfer is the concentration gradient. Like we can KLA into C star minus CL. That this is the gradient, and here also what is the gradient? T2 minus T1. This is the gradient. Here maybe V2 minus V1. That is, this is the gradient that forces we have. The resistance factor which will slow down the transport. The purpose of resistance means this slow down the kind of transport processes. As I point out, very interesting that a mechanism of transportation, that momentum, heat and mass transfer phenomena usually take place by two different means: molecular transfer and what you call convective transfer. And in case of heat transfer, another mode of transport is there, what you call radiation, which is not applicable in case of this mass and in case of momentum transfer. The radiation transfer is applicable only in case of heat transfer, and this is not it is not much important for momentum and mass transfer phenomena. Now let me explain more elaborately that what do you mean by that. Then let us I can give a small example that I can give a small example. Suppose there is a fire take place here. This is fire. So we want to extinguish the fire. So fire can be extinguished at that three different phenomena. One is, suppose we know water is the best media through which we can extinguish the fire. So we have bucket. This bucket of water I can transfer in three different means. How? One person can carry this one directly to this field. Another, the different person, they can stand here and they can hand over this bucket to one after another and transfer here. And another, we can use a pump. Here we can use a pump, and with the help of pump we can pass this water. So three different means we can do that. Now if you look at three different means at three different purpose. Now here that person is physically moving with the material. Am I right? This is with the material they are moving. But here the person is not moving, but material is moving. That 1, 2, 3, like this. And here with the help of pump you are doing this. This particular pumping, this can be explained with the help of what you call radiation, and these particular things, this may be considered as a conduction, and this is considered as a convection. Now molecular momentum, if you transfer, how we can calculate? Suppose there is a two plates. This is the two plates. This is one plates and one plates. The water is there, stagnant water is there. All of a sudden you move this bottom plates, then what will happen? The velocity of the fluid will be like this. It will be, the profile will be like this. This can be explained that with the help of Newton's law of viscosity. This is the shear stress, am I right? And this is the shear rate. So this is equal to mu into this. And what is mu? Mu is considered the viscosity of the liquid. So viscosity is basically nothing but shear stress by shear rate. The viscosity is the proportionality constant of the Newton law of viscosity. Measurement of resistance is gradually deformation of the shear stress. For example, honey has much higher viscosity than water, and also has dynamic viscosity. So here, if you look at that, pouring of water, this is water is pouring, this is water, and this is honey. Am I right? The honey has higher viscosity, so it is way it is pouring, it is a different way, that, and this is spreading very easily. So this is how we can explain that. Now momentum, as I pointed out, this is equal to mass into velocity. What is the unit of mass? Kg. And what is the unit of velocity? That is mass per unit time. So this we get then mass flux. The flux is always with respect to per unit surface area. So if the kg meter per second, then kg per meter second is the Newton per second, and this is usually expressed as Pascal. Now shear stress, that this is, I told you, this is shear stress is nothing but Newton per unit surface area. This is Pascal, and this is the velocity. Vx is the direction, because that if you look at this direction of flow, maybe of this is x, this might be y, or this might be z, and this might be y. That the different direction it can move. So this is the x direction. Y is y is mean meter, and viscosity is equal to Pascal per unit meter per second, and meters inverse the Pascal second. Now similarly we can find out what should be the unit for viscosity. That this is, I told you, this is shear stress by shear rate. If you give, we will get this equation. Now Newtonian fluid, what do you mean by Newtonian fluid? Fluid which obeys the Newton law of viscosity. That all gases, most liquid which have simpler molecular formula and lower molecular weight, such as water, benzene, ethyl alcohol, carbon tetrachloride, hexane, and most solutions of simple molecules are Newtonian fluid. So this is how Newtonian fluid can be defined. Now this is very important, that if you plot, this is shear stress versus shear rate. If you plot, and this is for this will be for Newtonian liquid, and this is for non-Newtonian liquid. These all are non-Newtonian liquids. So what is non-Newtonian liquid or fluid? The fluid which do not obey the Newton law of viscosity, called the non-Newtonian fluid. Generally non-Newtonian fluids are complex mixtures, slurry, paste, gels, polymer solution, all considered. Here we have given the example of beam plastics. This is actually happen in case of fermentation broth. Some fermentation broth, they behave like beam plastics. So this is also a non-Newtonian fluid. It is not Newtonian. If it is Newtonian, it will follow this one. Now convective momentum transfer, that I already explained to you what is convective. The transportation can be done from the bulk flow of the fluid, and that fluid center has the velocity Vx, then the momentum will be what? This is Vx into rho, the Vx into rho into V. What is rho into V? Rho into V. V is the volume, here volume, and rho is the mass per unit volume. Am I right? Mass per unit volume, and this is volume. So volume will cancel, this will be mass. The mass into velocity is the what you call momentum flux per unit volume, that can be explained. Similarly, the velocity y and z direction, we can have the momentum flux like this Vy rho V and Vz rho V. This we know that the flux, when multiplied this by the area perpendicular, we can calculate the force. This is, I have already shown you before. There are different boundary conditions that we have in this what you call solid liquid interface. There will be no slip flow, and in case of liquid interface, the free slip flow is there, and gas liquid interface, the shear stress of the gas liquid interface will be zero. That is how that is the boundary condition that we have. Now let us calculate the flow of the fluid through the circular tubes. Okay, that is the cavity flow. Now let the fluid constant has the fluid constant density rho and the viscosity mu be flowing in the circular tube of radius r, capital R, and length L. Let us consider the fluid is moving in the z direction, and hence Vz is considered. Vz is that velocity in the direction of z. Now the flow of the circular tube, the assumption, following assumptions we made. one is steady state condition. Laminar flow, we know that laminar flow occurs when the Reynolds number is less than 2100. If so I can tell you that 210 to 4000, it is transient, neither laminar nor non-laminar flow, that non-Newtonian flow, but below that it is Newtonian flow. At 4000 we have turbulent flow. This is laminar flow is less than 2100. The incompressible fluid, the density is constant and viscosity also constant. So on unidirectional flow, liquid flow only in the z direction, the v theta equal to 0 and Vr equal to 0. Newtonian fluid, no slip between the liquid and solid surface of the wall, no end effect. The disturbances of the flow of the liquid at the edge at the z equal to 0, z equal to L are neglected, and flow of the liquid is under gravity only. So these are the couple of assumptions we made to analyze this fluid. Now let me explain that flow through the circular tube. Now under this assumption that jet momentum is considered as follows, that molecular momentum flux is tie Rz, and the theta z equal to 0 and zz equal to 0, that we assume. Then here we also consider a segment. You can see that segment, this is the del R we consider, so just to integrate from R to R. So following the flow through the circular tube can be explained as rate of molecular momentum in across the cylindrical surface R, rate of molecular momentum out across the cylinder R plus R del R, and plus gravity force acting on the fluid, that should be equal to 0. Now rate of molecular momentum in can be explained like this. This is the surface area, am I right? This is per unit surface area, so tau Rz, this is R. Then this is the R plus del R, and this is the gravitational, this is rho g, you multiplied, you will get the gravitational force acting on the g direction of the fluid. Now combining this whole equation, we will get this whole equation, we will get this is equal to 0. Now we divide by twice by del R into L, and taking del R tends to 0, we get this differential equation that will simplify the R rho into G. Then we through integration, that if you look at here, this is like this. Now if you do the integration here, then what we will get, this is equal to C1 is the constant, am I right? This is constant. Then this is equal to, this is if you divide by R, you will get this equation, where C1 is the integration constant. So flow through the circular tube, what is happening if R equal to 0, center of the tube, the fluid velocity will be maximum. Suppose this is the tube, and you know that the velocity is the maximum here. Why it is velocity? Where you have less friction. As you come to the close to the wall, there will be friction between wall and the liquid. So you know that the velocity will be affected. So physically the molecular momentum, that flux, that is tau Rz, will be finite at the center of the tube. Now flow through again we can find out the boundary conditions like this: R equal to 0, tau Rz finite, I told you, and C1 must be equal to 0, otherwise the momentum flux will be infinity at the center of the tube. Therefore we can write this is equal to R tau Rz equal to R by 2 rho into Z. Applying the Newton's law of viscosity, we can find out this is equal to that we know this is, now this is already we have seen. Now we can write this equal to this, we can write this. That is exactly what we have shown here, and this is like this, then we can derive this equation that Vz equal to, then again this is C2 is the integration constant. Then again if we applied the boundary conditions here, r equal to small r equal to capital R, I showed you the small r here and capital R here, then Vz equal to 0, then the equation will be this, and then RC2 will be this, then combine this we will get this equation, and final equation will be, if you take this common, your final equation will be this. Now flow through the circular tube, the velocity profile in the laminar flow incompressible liquid, Newton flow, this is the velocity profile, because what I want to show, this, suppose the liquid is flowing through this pipeline, so it will be having like this. Now why? Because this is exactly why as the liquid comes close the wall of the tube, there will be friction between liquid and the wall, so your velocity will be retarded. So this is the parabolic velocity distribution that will obtain. The one important parameter that is used to characterize the flow characteristics of the fluid, that is the Reynolds number, and Reynolds number can be explained as du rho by mu. Am I right? So this is du we consider as a inertia force, and mu by rho we consider as the viscous force. So the Reynolds number is nothing but that the ratio between the inertia force and the viscous force. Now I was telling like this, that if the Reynolds number less than 2100 is laminar flow, it is more than 4000 we call it turbulent flow, and transition flow is if it lies in between, it is neither laminar flow nor turbulent flow, this is in between 2100 to 4000. This is the pattern that we have, that is in case of laminar flow clearly we can see the velocity gradient, and this velocity gradient can be minimized when we have the turbulent flow. When if the velocity of the fluid is maximum, then you can see that here the velocity gradient is reduced to a great extent as compared to the laminar flow. In this particular lecture we try to cover a new topic, that is transport phenomena in the bioprocess, and I told you transport phenomena plays very important role in the biological process, because it has three different approaches. One is momentum transfer, and the heat transfer, and the mass transfer. And basically that momentum transfer is applicable for the mixing of the fluid, because which is very much required as far biochemical industries is concerned, because how the cells remain suspension, how you add some kind of media, that ingredients to the media, how quickly it disperses. Then we have heat transfer, because organisms are very sensitive to temperature, so temperature is to be maintained. The heat transfer plays very important role. And mass transfer, I told you the aerobic fermentation process, we required to have proper dissolved oxygen concentration for the growth of the microorganism, because the oxygens are sparingly soluble in the water. So all these transport phenomena can be explained. But first in this particular lecture I try to discuss the momentum transfer, how different parameters involved with this particular things, and we try to correlate, we try to find out what is viscosity. Viscosity of the fluid is nothing but ratio of shear stress by shear rate. Then we try to analyze the system when it passes through the cylindrical tubes, and finally I try to point out that how the Reynolds number influence the flow characteristics of the fluid. If the Reynolds number is less than 2100 we call it laminar flow, if it is more than 4000 we call it turbulent flow, and if it is lies in between 2100 and 4000 we call it the transition flow. Thank you very much.